All right, here's our last video. We'll take a look again at what happens when we compare these two situations. So on the left, we started out with a weak acid. The pH was 2, or roughly 2 when we started, and we ended up with a pH that was approaching 13 because we added a strong base. And the only reason it wasn't higher than that is because now we've diluted the by adding the base to the acid. Our final concentration of acid is less than what we started with because there's just a lot of water there. So our pH is approaching 13 rather than 14. We compare what's on the right. We start out with a weak base that is in fact roughly a tenth, even less, maybe a 20th as strong as the weak acid in the first problem. So you see we started out with a pH that's definitely basic, but about 11.3 or so instead of closer to 12. But you can see the shape of the curves is the same, right? We decrease and we go through kind of a linear portion of the curve, considering that's a semi-logarithmic curve. And then we have this extremely sharp change in pH as we near the equivalence point. As we pass the equivalence point, the pH starts to change much more slowly and coming in at a very acidic pH because we're adding a strong acid. All right, now let's see what happens when we have a weak acid and a weak base. All right, they're going to react to some equilibrium state. We don't really know what that is. We have to do a little arithmetic, and we'll do that right now. We have hypochlorous acid, HOCl, it's a weak acid, and methylamine is CH3NH2 is a weak base. So we want to write the balanced chemical equation for the ionization of HOCl in water. So when we do that, it's a weak acid, so it's going to donate that hydrogen on HOCl and gives it to water, forming H3O plus and OCl minus. All right. Part B says write the chemical equation for the ionization of methylamine. Methylamine, being the base, is going to accept one of the H's that the water donates. So when we write that equation, we end up getting OH minus and CH3NH3 plus as products for this reaction. Now the question says, fill in the missing information. So we're given the Ka for HOCl, and we're given the Kb for CH3NH2, and we're asked to calculate the conjugate, the K for the conjugate material. So for HOCl and for OCl minus and for CH3NH3 plus, we've got to calculate those Ks. Now, we can recall that Kw is Ka times Kb. So to find the Kb for OCl, we're just going to take Kw divided by Ka. Okay, pretty straightforward. When we do, we get 3.33 times 10 to the minus 7th. And for CH3NH3 plus, the Ka is just going to be equal to the Kw for water divided by the Kb for methylamine. Again, a straightforward calculation, 2.27 times 10 to the minus 11th. Now the question says, write the balanced chemical equation for the acid-base reaction that occurs when these two mixtures or these two solutions are combined. One of them is going to be an acid and one of them is going to be a base, but the question is which is going to be which, okay? And as it turns out, this is the reaction that occurs. The HOCl donates its H and gives it to the CH3NH2 plus, okay? A student mixed 50 milliliters of 0.1 molar HOCl with 50 milliliters of 0.1 molar methylamine. Is the resulting solution acidic, basic, or neutral? Now we're going to really justify our answer in part D. Okay, so let's go through this. Won't take long. Whichever K value is the largest, that's going to dominate. That's going to tell us which of these things is acting as an acid and which of these things is acting as a base. So if you recall by looking at our chart, when I have to compare the Kb for OCl minus or the Ka for CH3NH3 plus, OCl minus is a significantly larger K by a factor of 10,000, right? So since we know that, the production of OH minus from the weak base OCl minus is more than the production of the acid H3O plus from the weak acid CH3NH2 plus. So on the basis of that, just looking at comparing the Ks, the pH of this solution will be basic, will be greater than 7. Okay, now we can use our knowledge of what happens to determine the concentration of an analyte in solution. All right, a student is given a sample of hydrochloric acid of an unknown concentration and performs a titration experiment to determine the concentration of what it is. So here is the titration curve that this student has. You can see she's adding 0.180 molar sodium hydroxide, and she gets a pH curve that looks like this. What can we get out of this? Okay. So part A, the student titrates a 20 milliliter sample of HCl with 0.18 molar NaOH. Based on the titration curve, what is the concentration of HCl? How in the world do we do this? Well, let's take a look here. And I just rewrote part A. So we can look at this curve, right? Even if we didn't know the identity of the acid and the bases as strong ones, we could look at the graph, right? We could see from the graph the midpoint of the titration curve is at 7. And there's a 4 pH units below where it starts to bend and 4 pH units above where it starts to bend. So it tells us that neutralization occurred at a pH of 7, which is a characteristic of a strong acid, strong base. Okay. Now, the volume of sodium hydroxide that was added is 30 mils, because we can look at the graph and see the green line and go, well, that's how much I added. And we know that at the equivalence point, moles acid is equal to moles base. And we can get moles because we can multiply the volume in liters times the molarity in moles per liter. So we would write that as volume of acid times molarity of acid is the volume base times the molarity of the base. Okay, we want M sub A, the molarity of the acid. So we just rearrange that equation and we get molarity of acid as the volume of base times the molarity of the base divided by the volume of acid. So we do in the math, it's pretty straightforward. Now you can see if I rearrange this, this is really 30 divided by 20 times 0.18. Well, 30 divided by 20 is 1.5. So 1.5 times 0.18 is 0.27 molar. Pretty straightforward. It didn't look straightforward, but it actually is. Okay. Now, the last part of this question says we want to sketch the curve on the graph below to represent the expected titration if the student titrates a 10 milliliter sample of the HCl solution with 0.18 molar NaOH. Okay. Now, here we have the same molarity as before, but instead of 20 milliliters of HCl, I only have 10. So because I have half of the volume, it's only going to take half of the volume of NaOH to neutralize it, because we're working on moles. And before, this was a strong acid, strong base. It's what we have again. So now our titration curve is the same shape. It's just lined up on 15 milliliters. So our curve looks the same. It's just been shifted to the left. Okay. Now here, we're going to do the same thing, but we're going to double the volume of HCl. We went from 20 to 40. Well, if I double the volume of, double the number of moles of HCl, I have to double the number of moles of NaOH. And if I use the same concentration, I have to double the volume. So my curve ends up on 60 milliliters for my equivalence volume. All right. Lastly, a student is given a sample of formic acid, HCO2H, and we want to, well, let's see what we were tasked with doing. The student titrates a 50 milliliter sample of HCO2H with 0.2 molar NaOH. Based on the titration curve, the concentration, they want us to compute the concentration. All right, we look at this, we see where the equivalence point occurs. It occurs at 25 milliliters. All right, so I can easily compute these numbers of moles, but in this case, I use the same equation. Volume of acid times molarity of acid is volume of base times molarity of base. I want the molarity of the acid, so now it's just 25 over 50 times 0.2. Well, 1/2 of 0.2 is 0.1. Okay. Now, we also, oops, I got my little answers put in out of order. We're also tasked with finding the Ka. Now, recall, pKa is at our half equivalence point. So we can look and see, where is our pKa occurring? All right, so pKa is at 3.75. We know that because the problem statement tells us that. Okay, the pH of the reaction mixture is equal to 3.75. Use this information to calculate Ka. Well, at this point, Ka is just going to be 10 to the minus 3.75, because at the half equivalence point, pKa is equal to pH. And so we just do the logarithmic conversion and we get 1.78 times 10 to the minus fourth. We round that to 1.8 times 10 to the minus fourth. So even from curves like this, we can get our K values, when before it didn't seem like we could. It's pretty straightforward to get a K value. Okay, so here are curves. Our data points are pretty easy to find. It's pretty easy to get this information off of these curves. All right, if you've got questions about this, go back, replay the slides, replay the video, stop and do the calculations for yourself. And if you've got questions, ask me in class.